Hey there, Calc folks, back here with another video in our study here this semester. This video is kind of off the beaten track, I will tell you that. I want to look a little bit at some exponential models. One of the topics that is in our syllabus, and one of the goals that we have to make sure that we prepare for is getting through perhaps a differential equations course. Where in a differential equations course, we are going to spend a little time exploring exponential models. Their corresponding differential equations built with exponential models behave kind of uniquely. So we want to be familiar with this modeling process when we get up into those courses. So built into this course is just a little exploration into exponential models as we move forward here, where I don't really have a lot for you on this. You'll notice there is a section in the book prior to this that does discuss all the calculus and the algebra involved with exponents and exponential function types, exponential and logarithmics. Take note, I'm not going to spend any time there because that is considered review material in this course. But I do want to get into looking a little bit at algebraic technique with the modeling. And that is what this lecture focuses on, is that algebraic technique with the modeling, folks. If we flip over here, we'll see what we're talking about. We are talking about exponential models. And I do take note to begin with here that every value illustrating either exponential growth or illustrating exponential decay can be illustrated by an exponential model described by what I illustrate here on the screen, right? It can be described by this functional model f of x, right, where x is the independent variable, which is equal to y null times the value of e being our natural number, raised to the power of k times x. Right? Again, this is where e is our natural number in this model. Right? It is about 2.71828 in value if we were to go out to several decimal places. Right? Y null in the model is what's known as the initial value of the function. As noted, x is the independent variable. And if we make x equal to 0, you will have k times 0, or 0 as this power, and you will have e to the 0 power, which is equivalent to 1. So you will have 1 times, this will be 1, times y null. And 1 times y null will just be y null. So y null is the value of our function f at null, or at 0. And it's known as the initial value of the exponential relationship, or of the function. All right, and k is the what we call rate of the rate constant. It is the constant of the rate of change in the exponential modeling here, folks, and it varies from model to model depending on how quickly that exponential growth is occurring. Right? We have the case for growth when that rate constant is certainly greater than 0, and it is the case for decay when that rate constant happens to be less than 0. Right? In one case, you will see exponential growth happening, and in another case, you might see here exponential decay happening. So that would be starting up here and decaying. Right? Starting up here, and you might see decay happening exponentially. That would be the case for k less than 0 in our model. All right? If we look at a specific example of this, all right, what we're going to do here is assume to begin with that we do have this function f of x that's illustrating exponential behavior. All right? It's going to illustrate what we think of as being able to be modeled with the exponential model seen above here. where we aren't given initially that specific model, but we are given a few pieces of useful information. We are told what the model would yield as its value when the initial value is 0, right? When the value of x is 0 in our model, right? We are told in a sense what is our initial value, and we are told also what is the value given by this model when our x value is 3 in value. With these two bits of information, I have enough information to actually build a model, right, as we've seen given here above. Now, as noted in the model seen above, x is certainly going to be our independent variable. What we're going to need to identify is the values of y null and k. Y null being the value of the function f at 0, which we are actually given. That is the value of 100. What we are not given, however, is the value of k. What we're going to use is this piece of information, the fact that f at 3 is equal to 480 in value for this model, right, to actually help us find that value for k. All right. If we take note, right, with the given information, we know, if we start to prepare this model here, we know f at 3, which is going to equal 480, must equal 100 times e raised to the power of k times 3, right? 3 being the value of x, right, where we're evaluating our function f to obtain 480 in value, and 100 being the initial value of f in our relationship here, right? With f of 3 noted to be 480, and understanding that 100 is our initial value, we are able to prepare the fact that 480 must be equal to 100 times e to the 3 times k value. Where if I divide both sides by 100, that does imply that 4.8 must be equal to e raised to the 3k power. Or if I apply the natural log to both sides and divide by 3, k must be equal to 1/3 the ln of 4.8 in power. Solving for k, I can find that the rate constant here is given by the exact value of 1/3 the ln of 4.8 in value, the natural log of 4.8 in value. All right. So in terms of my model, I can substitute that value back into my model, right? And we see here that f of x is going to equal 100 times e raised to the power of 1/3 the ln of 4.8 times x in value. This is the exponential model, right, described by this behavior seen in the model, right? This initial value, right, and this, right, observed value after our initial state, right? The observed value at the value of 3. This observed value at the value of 3, along with the initial value, can be used to solve for k in our model. Right? You do need the second point. Notice that just does not work with the initial value because that is where k is equal to, or x is equal to 0, and k times 0 will 0 away for any value of k. Whereas for at 3, right, that k is going to remain part of the equation, and we can solve for it using our understanding of what inverse functions for exponentials being logarithmic in behavior. All right, using just a little bit of algebra, right, for transcendental functions. Now, I do think I get into an analysis of half-life here. Let me see, right? Or double time in half-life, we should say. Doubling time in half-life. Excuse me. If we are interested in the time it takes for the exponential behavior to, for instance, double, right? We are interested in the value of x. We might say x equal to x sub 2, right? Where twice our initial value f of 0 would be equal to our initial value f of 0, again that being 100, right? Being times by e to the 1/3 power, e to the 1/3 times the ln of 4.8 times this x sub 2 power, right? Where f sub 0 would be equal to 200 in value in our case because our initial value is equal to 100. I write it this way just to illustrate that what is going to happen is we can divide both sides by f of 0, and that will disappear, right? We can divide out that 100 from both sides. That is going to leave you with 2 equal to e to the power of 1/3 the ln of 4.8 times this doubling time that we're interested in, x sub 2. Where to solve for x sub 2, we can apply the ln to both sides, right? That will give us the ln of 2 equal to this power, right? And then divide both sides by 1/3 the ln of 4.8, and we will solve for x sub 2. And the doubling time, x sub 2, equal to 3 over the ln, or 3 times the ln of 2 over the ln of 4.8, right, is going to be approximated by 1.32565 in value. All right, but this is the length of time that needs to elapse in this exponential model, right, for the values in the model to double in their value, right, for the values modeled, right, by the functional exponential model here that is functional to double, right, by the functional model to double here. Notice if we evaluate the function at this value, right, if we evaluate f at x sub 2, right, f at the ln, or 3 times the ln of 2 over the ln of 4.8, and we substitute that into our model here for x, you will get some canceling happening, right? The 1/3 will cancel with the 3, the ln of 4.8 will cancel, and you'll be left with just the ln of 2 up there, right? You'll have 100 e to the ln of 2. Now, e to the ln of 2 is just 2. So you'll be left with 100 times 2, which is 200 in value, indicating that if we start at 0, it's 100, and if we allow x sub 2 to elapse to its given value, or if we allow x to elapse to x sub 2 here, the given value, right, by 3 ln of 2 divided by the ln of 4.8, we will see that the value given by this functional model will be doubled, right? It'll go from 100 to 200 in value, right? You can see that this change in your output of this function doubles over that change in input values. All right. We note that similarly here for maybe f of 3. We know f of 3 is equal to 480. And note, if we take f at 3 plus that doubling time, we should obtain 2 times 480, or 960 in value. We should see the function output double in its size if we add x sub 2 to that point in time at 3, right? And notice f at 3 plus x sub 2 is going to be f at 3 plus 3 times the ln of 2 divided by the ln of 4.8. Where if I organize that, right, into my model as an input value of x, I will prepare this as my exponent, where if you distribute this value, you will get the 3's to cancel. What happened here? This should be 4.8, not 4.9. Plus the ln, the 1/3 and the 3's will all, and the ln of 4.8 will all cancel back here, leaving you with just the ln of 2. Right? Where the ln raised to the power of this term plus this term is really just e to the this power times e to this power. And e to the ln of 4.9 is just 4.9, and e to the ln of 2 is just 2. So this really is just 100 times 4.9 times 2, or 960 in value. We see that doubling of the function when we add x2 to the independent variable value of 3, right, where we observe 480 in value. Right? Doubling time there, folks. That's, again, this algebraic process, right? And you can see these exponential models really don't involve a lot of the calc skills that we've learned up to this point, derivatives and whatnot. But it's a bit more of an algebraic process and understanding here. And it's working with those exponential functions and logarithmic functions and this inverse behavior between the two. All right. I do believe I formally defined doubling time. Yeah, in general, the doubling time is defined as follows. Right. For f of x equal to this exponential model that we've established up above, y null times e to the kt, right? The doubling time is constant, right? And given by x sub 2 equal to the ln of 2 over the absolute value of k. All right. In this case, the decay, right? If we want to talk about decay, in the case of decay, when k is less than 0, x sub 2 is actually then known as the half-life. Right? It would be the case for half-life. Either doubling time or half-life, with time for it to cut in half in the case for decay. But in either case, it's just going to be the ln of 2 over the absolute value of whatever your rate constant is for the case of either exponential growth or exponential decay. All right? In the case of decay, we don't get doubling time, we get half-life. All right? I do believe I look at a half-life scenario here. All right? Suppose f of 3 equals 250, right? And f of 9 equals 125, right? Where we can see that the half-life of this exponential model here, this model that must be illustrating exponential decay, right, is x sub 2 equal to 6 in value, right? 6 units have to elapse in our value of x. We might add that in there. What we see happen here is this is 9 minus 3 in value is equal to 6. Right? The half-life measurement is 6 in this case. Right? Implying, right, that x sub 2, the half-life measurement of 6, must be equal to the ln of 2 over the absolute value of k. Or that the absolute value of k must be equal to 1/6 the ln of 2. Where if we solve that for k, that is going to imply that k is equal to plus or minus, right? It's going to be equal to plus or minus 1/6 the ln of 2. Right? And furthermore, since f illustrates decay, we can conclude k must be equal to that negative 1/6 quantity. Right? 1/6 the ln of 2. Right? Negative 1/6 the ln of 2. And thus, when we think about our function f of x must be equal to y null, right, times e to the negative 1/6 the ln of 2 times x. Where I can now use this information to go about solving for y null. All right? As for determining y null, f of 0, right, we might note the initial value of the model, right? To determine the initial value of the model y null, since f of 3 is equal to 250, we can say that 250 must be equal to y null times e to the negative 1/6 the ln of 2 times 3, or negative 1/2 the ln of 2, if we simplify the 3 with the negative 1/6. Implying that 250, right, must be equal to y null over the value of e to the ln of the square root of 2, because negative 1/2 would move that to the denominator, and the 1/2 could move inside the ln as a radical, which we can write as such. Right. And the e to the ln will then cancel, giving us 250 must be equal to y null over the root 2, further implying that y null must be equal to 250 times the root of 2. All right. This being our value for y null, we can then substitute that back into our model, and thus the model illustrating this exponential decay must be the model seen here. Right? Our value of y null being the 250 times the square root of 2, our rate constant k being negative 1/6 the ln of 2. Right? The rate constant found by taking note of what was our half-life, and then y null being found, right, by solving for y null when we know our half-life using one of the other coordinates that happen to lie within this model, having to use one of our other observations for x and f of x that happens to lie or be given to us initially in this model. All right, folks. This is exponential model problems. You need to become familiar with every exponential relationship, right, can be modeled in this manner. All you really need is 2 observations, right, of that exponential behavior. And if you have 2 observations of that exponential behavior, you can always model, right, as we have seen above here. All right. And then likewise, you can find things like doubling time and half-life, respectively, or even tripling time and, right, the respective in terms of decay. Right, using just some algebraic tricks, right, folks, or algebra. Really shouldn't say it's tricks, it's algebra, folks. Working with exponential and logarithmic functions, natural log and the natural exponential function specifically, right? This is how they model exponential behavior in the world around us. Currently, we're in this pandemic situation where certainly very early on, the spread and the growth of this, the number of people infected by this pandemic was exponential, right? And all we needed were a couple of observations of the number of people infected over a unit of time to build the beginning of this model, right, where we were seeing the exponential growth. Right. Very early on in that model, we were trying to flatten the curve by making our growth rate not so quick, right? Not so large in value as we modeled, right? Or as we were experiencing this pandemic, right? So, folks, this is what we're looking at here is, again, exponential models, and you just need a couple of points, a couple of observations in the model, and you can always use, right, this, right, functional relationship seen here, where e is the natural exponential function to model that exponential growth. And that is what is nice about e. That is what's special and so interesting about e, right? It is the case for constant growth. It really is a measurement of exponential growth that looks at the rate of constant growth, right? And as a model, helps in the model of rate of constant growth. And that's what we expect in the natural world around us is when things are growing, is that growth to be constant. It doesn't grow in choppiness. It grows in, right, a nice smooth manner when we are experiencing growth. All right. So, folks, that is this set of notes. I'm at about the 25-minute mark, and that is about how long I like to try to make these shorter lectures. So I will end here, but this is what I want to give you here on exponential models. So with that said, I'll see you in class, and I'll see you next time.